Okay, the next few videos will I will discuss Numpy, which is the very popular package for numerical Python. Actually, Numpy is like list, but it is much faster than list. One restriction, if we restrict the list, remember a list actually is a collection of a lot of data objects that was so abstract as we saw in previous videos. If, for example, we restrict a list that all the objects, they must have same type, all the elements in the list, for example, they have same type, then that list with all the same type, that is what the NumPy looks like. But NumPy is way more faster. And the reason is, even if you define a list with all the elements that are, let's say, of same type, but because list in abstract way can handle heterogeneous kind of objects, the functions that we will apply on these items, they will no longer be faster. Further, to store each element, we have to store the information or metadata for that element. In NumPy, it is both. It is efficient with respect to memory, because if the type is same, we need not to save information about each element, because we need just to save the information about the type, because the type is same for all elements. Further, when the type is same, we can write functions that are much more faster than list. So NumPy is very popular. It has very fast universal functions available, the methods that are available in NumPy, and it's a package. It's a whole directory structure containing a lot of packages inside, a lot of modules, and so much. At the end of the day, it's simply, or in layman terms, it is like a list with all the same type objects, and it is much more useful when all these objects are numeric type. Although you can have a NumPy array with string data types, all the strings or all general objects as well, but the power of NumPy array will become much more evident when we will be working on numeric type data. So in this particular course, we will focus more on numeric data than other kind of data. So that's how you write import. NumPy is installed, or if you have installed Python using Anaconda, NumPy is already installed there. It is in the site packages, kind of a built-in package. So import NumPy, we can stay as it is, but we can rename this NumPy just NP. That's most popular name. We can write any other name, but if you see the books or internet or somewhere, this NP somehow becomes much more popular. Okay, now we can define an array, for example, np.array. That's array is just a method of np, kind of function. And we can define an array using list. This is the list of several numbers. Or we can define array as a tuple as well. So whether we give a tuple, whether we give a list, an array is defined, and then we can see the contents of this array, this NP array. So let's just go to our friend Jupyter Notebook and get our hand well gripped on this NumPy. So first of all, we need to import NumPy package, and we may rename as, for future use, as NP. So let's say that is imported. So now let's say A is an array. Let's say np.array. That's a function, and we may have a list inside. Let's say 1, 2, 3, 5, 7. Let's say that's array. We can also define the array using a tuple rather than a list. It's our choice which way we define the array. Either way, 2, 3, 5. Let's say that's another array, for example. So if we print, for example, A, it will give us A, but if we just see the type of A, it will no longer be a list. It will be an ND array, numpy.nd array. That's an n-dimensional array. Okay, great. So there are so many attributes of this A and this B. Similarly, if we see the type of B, although we have defined this B using a tuple, but the type is the same. It's a Numpy object rather than a list or a tuple. So that's how you can create the array. One more thing that is important is to check the attributes of A. For example, A dot D type, that will tell us the data type in A. So for example, A stores all the data that is integer 32. At define time, for example, we can specify the data type if we want. We can specify D type if we want. For example, integer. That means A is integer. Here we can define, for example, D type as float, for example. So data type becomes float. There are several other options that are available to define the data type. But even if we don't define, the data type can be defined automatically based on contents. That's what the dynamic typing means. So if we now define type, that's this. If we now check the type of A, that is again integer 32. But if we check the type of B, D type, that might be a float number. Yes, that's float 32. Again, there are 64-bit support as well. I mean, we can define here. There are several options here available. So that's how we can define the NumPy array. That's just getting started with NumPy array. In the next video, we will play with these arrays a bit more. So hope to see you in the next video. Okay, in the last video, I introduced NumPy and we actually declared a NumPy array using a list as well as a tuple. In this particular video, we will be seeing some of the properties of the NumPy array variable, or sometimes called the object, that variable. So there are several properties, but I will discuss, for example, last time I discussed one property which is D type, A dot D type. And that actually stores the information of the data type of the elements of the array, of NP array. Remember, NP array, all the elements of NP array, they must have same data type. It cannot store heterogeneous arrays as it is. Okay, now there is another property sometimes called the dimensions, or ndim. That tells actually what are the dimensions of the array. I need to explain this term dimensions with the following example. Let's say, for example, that's an array. Just consider that's a list, for example. 1, 2, 3. That's one list. And if it is an array, for example, if this is np dot array. With that list, we will say that array as a one-dimensional array because we only need one index to access that. For example, if you need to access any element in this array, you only need one index, either 0, 1, or 2, only one index. That's okay. So in this case, we have just one-dimensional array. On the other hand, for example, if you see here, that's one array or one list, that's another array, another list. And that's another list that contains lists inside. For example, let's say that's array 1 and that's array 2, and that is simply an array of two different arrays. That's an array and that's an array. For example, A1 is this array and A2 is this array. Now, if we need to access any element in this particular array, we need two indices. First of all, we have to locate whether we are going to talk about A1 or A2. We need one index for that. For example, if we want to locate A1, that means we are going to access with element 0. Let's say this whole array is A. So first of all, we say OK. 0 means we are going to access from A1 and A2 one of those. So 0 means the first one. OK, now A1. Now inside A1, which element? This is the 0th element, this is the first element, this is the second element. Let's say we want to access the first element. So that means we are talking about this. So very loosely speaking, the total number of indices that are required to access an element inside the array is called dimension of the array. An ndim that actually defines that actually describes this property, the total number of dimensions. Consider, for example, this is a 2D array or two-dimensional array. Let's say that's a two-dimensional array A1, and that's another two-dimensional array A2. That's another two-dimensional array A3, for example. And let's say this is an array of two-dimensional arrays. Let's say np dot array. Now that whole array, whatever that array is, a three-dimensional array, and the reason is to access any element we need three indices. First index will define which one of these we are selecting. For example, let's say we are selecting that, so one index is needed. That index is 1, for example. Then inside this structure, like so, we need two more indices to locate a particular index. For example, because A2 is a two-dimensional array, it has two one-dimensional arrays. So which one-dimensional array you are, it has many one-dimensional arrays. So which one-dimensional array you want to pick? Let's say the sixth one with index 5. Now you have located the sixth array. Now in that array, what element? Let's say the 8th element. So we need three indices to access a particular element. So the dimensions of this array is 3. So let's play with that in Jupyter Notebook just to get more comfortable with the term dimensions. So let's say, for example, we have an array A. Let's say A is np.array, and let's say it contains a list, let's say 1, 2, 3, and then we have another array, one-dimensional array, let's say 4, 5, and 6. That's another array, and that is an array of these two arrays. So that is basically a two-dimensional array. It is array of arrays, list of lists equivalently. So that's A, for example. Oh, what's the problem? Oh, we haven't imported Numpy. We should have. So import Numpy as np. Okay, we need not to import that every time. Actually, I'm recording this video after a few hours, and I have restarted all these things, so I have to import now for the first time. But once imported in the notebook, as long as the notebook is running, you need not to re-import anything. Okay, so a dot, for example, ndim, a dot ndim. So that is 2 here because there are 2 dimensions. For example, if I want to access element number 3, this element, so this element is located in the first array of the 2 arrays, which has, so the first array, there are 2 arrays with index 0 or 1, so I am going to look into the first array, which is 1, 2, 3, and in that array I'm going to look for the element number 2, element with index 2. So that's how you can access the elements of multi-dimensional arrays or arrays with more kind of dimensions. Let's say we have another array, just to get more familiar with, np array, let's say, and we have a list, and that list actually contains 3 one-dimensional arrays. Not only that, actually, I'm confusing you a lot. Let's say we have 1, 2, 3. Let's say we have 3 one-dimensional arrays. Let's say we have another 2, 4, 5, 9. The sizes of arrays maybe different. Yeah, is that true? Maybe different? Yes or no? Let's see. For example, the first array has size 3, and the second array has total size. Is that okay? I guess yes. And now if we want to access, for example, an element with let's say I want to access this element 5. So that is in the second array indexed with 1, and then in that array it has index 2. So I've accessed this element. Oh, why not? Too many indices for an array. Why? Why is that? Why too many indices for an array B? So let's say B dot n dims, and then that is 1. Why one dimensional? I have I have this one dimensional array, and this is another one dimensional array, and I have made a list out of it. I mean, this is 1D array and another 1D array. I've concatenated them together. So I should have accessed this element. The problem is when you are going to define multi-dimensional arrays, the number of elements for each dimension, they should stay consistent. For example, if the first array has 3 elements, the second array must have 3 elements. Or if the second array has 4 elements, then the first must have 4 elements. If that is not the case, the array will not be defined like a multi-dimensional array. For example, if we, for example, extend our first array with, let's say, -1, now B will be having 2 dimensions, no problem. And now we will be able to access, for example, this element 5 like so. So we will go to B again. We will say, okay, select array number 2, and in that array, select the value indexed by 2, which is 5. So accessed, no problem. And that stays true if you're going to define, for example, a 3-dimensional array. Let me just give you an example of 3-dimensional array. Let's say C equals np dot array, and let's say we have 1, 2, and 3, and then we have another array, for example, 4, 5, 6. Remember all. So let's say we can have one more. For example, we can have one more list. Why not? So let's say we have 0, 0, -1, let's say, and that is a 2-dimensional array. Yeah, that's a 2-dimensional array. Great. Let's say we have another 2-dimensional array. Let's say we have another 2-dimensional array with same kind of consistency, the number of elements and stuff. Let's say these elements are all minus of the other ones. Let's say this minus, 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 and this is +1. And now we have this. If you see this thing, that's a 2D array. That's a 2-dimensional array. That is also a 2-dimensional array. An array of 2-dimensional arrays is basically a 3-dimensional array. Now that's a 3-dimensional array. This one. C. So if you we have some. I should have defined this with commas rather than spaces. Actually, yeah. The reason I did that is MATLAB. I worked in MATLAB also. So MATLAB allows this space-separated lists, but I just confused the things with Python as well. But Python requires comma there. Okay. With MATLAB, by the way, just as a side note, MATLAB allows you to have commas as well as spaces, but this Python is just restricts everything to comma. That's great. Okay, that is C. So now if you check C.ndim, that is 3. If you, for example, want to access this particular element, what should you do? First of all, you select the one of the 2D arrays. There are 2 2D arrays. So this is the first 2D array, and that's the second 2D array. And if you, for example, want to access this particular element, which is -3, if you want to access that, you first have to access one of the two-dimensional arrays. So let's say I access the second one with index 1. Now you are in this particular 2D array. In that array, which 1D array you are talking about? So I'm talking about the very first 1D array. So the very first 1D array is indexed by 0. And in that 1D array, which element you are talking about? So I'm talking about this element that has index 2 in this particular array. So now if you press enter, you will get -3. Wow. So that is basically how, and by the way, you can make a 4-dimensional array. A 4-dimensional array will be an array of 3-dimensional arrays, and so on. You can make, for example, n-dimensional arrays, and that's one reason why we call this as ND array. n-dimensional array. Now, the type of C is ND array, n-dimensional array. You can add as many dimensions as you want. Great. We will continue exploring this NumPy more and more in the upcoming videos. In particular, I will talk about this shape property of this NumPy. We have already discussed D-type, we have discussed ndim. In the next video, we will talk about shape, and we will discuss more about the NumPy. So hope to see you in the next video. Okay, in the last video we discussed this number of dimensions or ndim property of any NumPy array, and we also saw an example of defining a three-dimensional array in Jupyter Notebook. Let's discuss another property, which is the shape property. Let's see what this shape actually represents. So let's go to Jupyter Notebook and see what actually this shape represents. For example, you have seen this C as, in the last video, we defined this C as a three-dimensional array that contains two arrays of 2D, and each 2D array contains three 1D arrays, and each 1D array contains three elements. So what do we mean by shape? So if we just say shape, what is that thing? So shape is 2, 3, 3, and let me tell you what that means. The return is tuple, so that's a tuple that is returned, 2, 3, and 3. This 2 means how many two-dimensional arrays are there. Here we have 2. So in each two-dimensional array, how many 1D arrays are there? Well, 3. In each 1D array, how many elements are there? Well, 3. So basically this C.shape 0 tells you the total number of two-dimensional arrays, that is 2. And this shape, for example, 1 tells you in each 2D array how many 1D arrays are there, these many. And this shape, for example, 2 tells you in each 1D array how many elements are there. Well, 3. Great, that's awesome. Yeah. Can I tell you one strange kind of thing? You can define a NumPy array, for example, A as np.array with just one element, let's say 2. That's an array. Great. What's the number of dimensions here? What do you think? What is that? Is that a 1D array? What are the number of dimensions? Strange. It's a 1D array. Yeah, it is. See another thing. For example, B is equal to np.array, and you define it with, let's say, 3. And what are the dimensions of B? It looks like the same. The dimension of B should be 1 as there. The dimension of A is 1. It looks like the dimension of B is also 1. No. It's 0, because that's an array. If you pass it as a list, it's an array of 1D. If you just define just one number that can be defined as an array, NumPy allows you that, but that one number is just a 0D array. Now, if you concatenate a lot of 0Ds, you get 1D. If you concatenate a lot of 1Ds, you get a 2D. If you concatenate a lot of 2Ds, you get a 3D, and so on. Get a look and feel? Yeah. So that's what it is. So yes, in this video I discussed the shape. There are so many properties. Let me discuss some properties. Let's say size. That actually tells the total number of elements, complete total number of elements in the array. So how many elements are there? That is size. There is also, I guess, n bytes property. That tells how many total number of bytes that this structure is taking inside the memory. And there are several other, properties. If you just apply a tab and get certain things, you will see a lot of functions, and you can check a lot of properties. That some of these functions we will explore later on. Sometimes they are called the universal functions. We will see them because they are very, very fast. And these functions, the vectorized implementations of these functions, that is the reason why NumPy is so fast and why it is so popular. Anyways, so in the next video we will go to explore the NumPy a bit more, and we'll show you more fun stuff with NumPy. So hope to see you in the next video. NumPy actually provides a lot of functions to create arrays, special kind of arrays just for testing, and sometimes just for, I mean, there are a lot of ways to create arrays from scratch. For example, what if you want to create an array containing all zeros? So there is a function in NumPy, np.zeros, that tells you how to do that. Similarly, if you want to generate a lot of generate an array containing a lot of ones or all ones, there is a function to do that, and stuff like so. There are some functions that are actually used a lot, and I want to discuss those. One function is np.arrange. Actually, this is a single R. This is not a two R's. This is a single R. np.arrange with one R. And np.arrange function, what it does is it creates an array. For example, if you say np.arrange, it creates an array. For example, if you say okay 100, so it creates an array that it creates a 1D array that starts from the values in that array starts from 0, 1, 2, all up to 99. So that's an array. That's a quick way to create an array with all the numbers till 100. Yeah. So let's see a running example of this np arrange method in Jupyter Notebook, just to get a better look and feel of how it works. So let's see. So let's say we have a equals np.arrange, and let's say 100. So that's it. If you want to see what is inside a, you can see this is an array with all the values starting from 0 up till 99. Maybe you want to create an array that starts from a particular number, ends at a particular number. Maybe those two numbers are different, and maybe this arrange function actually allows that. Let's say I want to start with 20 and I want to end at 100, and I want to create all the array that does that. So let's say this. So that's okay. Start from 20 and at 100, but the last element, last index is not included. That's possible. Last but not the least, if you want, for example, to start from 20 and at 100, and let's say you want to take a jump of 3, that's possible. Remember, does this resemble with something that you know already? Remember that? Yeah? Let me pause for a minute. Not for a minute, just for some seconds. Let me pause. Do you remember this arrange, np.arrange function? It looks like something like what? Remember that? For I in range, yes, for I in range, for example, start from 20, go to 100, take a jump of 3. Remember that? So it has some resemblance with range function. Yeah. Although range is an iterator. What's an iterator? Why I'm telling you that? Okay, let me tell you an iterator as well here. Just spend a few seconds on this range function. You might be thinking, when we call this range, let's say starting from let's say range 10, you might be thinking that it returns a list of numbers starting from 0 to 9, but that doesn't happen. It returns nothing. Actually, when you actually call it, it returns just an object. When you call it in a for loop or somewhere, it progressively returns one by one, element one by one. So it returns an element, then it iterates and return another element. Then it never creates a list of elements. It never creates a list for you. That's awesome. Actually, it generates numbers. It generates the next number and the next number as you move on. So it saves a lot of memory. And these kind of objects, they are called iterators that iterate. They never create. But if you want, for example, to get a list, if you really want to get a list, then what you can do is you can call the range, let's say the same way, and you can just write a list. So provide me a list, don't just provide me an iterator, and that will give you a list. How cool is that? Great. Anyways, that was just a side note. It has nothing to do with this arrange function. Anyways, so np.arrange, it actually returns an array. It is not it is not like an iterator. It returns an array, complete array, the way you want. So that's what this arrange is. It has resemblance with this built-in range function that mostly used in for loops. Okay, next let's discuss this np.random.permutation. np.random is a package. Np is a package. It has a lot of sub packages inside. Random is a package. Random has a lot of modules. One module is permutation. There are a lot of other modules. So let's see this random. Let's see what it does. So for example, let's say a equals np.random.permutation, let's say permutation, and what I do is I say okay, np.arrange, let's say 10. What it does is this np.arrange will return an array containing all the values 0 to 9. These are 10 values. And then this permutation function that resides in the package np.random, that is in the random package of np, it actually shuffles all the values and rearrange all the values in random fashion. And a will now be an array containing the same elements but in a different order, in a different random order. So let me now print this a. It will be having all the elements from 0 to 9 but in a really shuffled way, and that shuffling is completely random. Yeah, you see that? Sometimes you may call some function, you may want to write some function on arrays, and you may want arrays that do not have a particular ordering, that are just random arrays, just to test your code, just to test how it works on any kind of array. In that case, one way of getting a shuffled kind of array, one quick way is to just use np.random.permutation function. The np.random package does not only have this permutation, there are a lot of other functions. np.random, for example, np.random random.rand int, for example, rand int, that creates a random integer. That's for example, if I let me call this, and we have how can it be used. Okay, we can give a low value from where we start, we can give a high value, and it creates actually random integer starting from low ending at high. So that's how it can be used. For example, let me call it as np.random.randint, create a random number between 20 and 30, create some random integer, and it will return some random integer between 20 and 30. If you call it again, it may return some other it is returning 30 again, 29 again and again. Now it returns 29, 22. Maybe we want to generate random integer between 20 and 30, so it creates a random integer. One thing that you might be noticing, what is the return value? The return value is v, for example. What should be the type of v? What do you think? Is this v is an array? No, it is a number. It's an integer. The type of v should be an integer because it is returning a random integer. It is returning an integer, but it is selecting that integer randomly from 20 to 300. So it should be integer, and it is. Yes. Wow. Yeah. So we will be exploring some more functions in the random package of NP, and then we will be moving towards this fascinating function called reshape. So there is more to come for Numpy. So hope to see you in the next video. Okay, in the last video we saw a range function. That's a very useful function to just create a testing array and just see output of a particular operation or algorithm just on different kind of arrays. Further, we saw permutation function in np.random package, and we saw that this permutation function actually it reshuffles, it shuffles different kind of if array is applied to this permutation function, it actually shuffles all the elements of that array in a random way, in a completely random way. Today we will explore this random package a bit more, and then we will see a reshape function, what that reshape does. Basically this reshape, for example, if we have an array, let's say array is, let's say we have an array with, let's say 10 elements, and if we call a dot reshape and we give, let's say 2 by 5, so it will make a two-dimensional array out of a, which is b, and that will be a 2 by 5 matrix, or that will be an array or a matrix with 2 rows and 5 columns. And now we can just work with this b just like it's a two-dimensional array, and we can just treat this b as a two-dimensional array and work with that. It becomes handy sometimes if, for example, we want to test certain operations on matrices. A quick way to make a matrix is just to call a range function, and then whatever the result is, just reshape it into the desired order matrix and test the algorithm. So let's go to the Jupyter Notebook and check this random package a bit more, and then see the reshape function. So let's go to Jupyter Notebook. Yes. So there are a lot of ways to generate these random numbers. One, for example, we already have seen rand int. Another way, for example, array A can be generated like np.random.rand function. So now if we create this, if we pass, let's say 1,000, a random value array will be generated in A, and each value of A will be a random number between 0 and 1. So all these numbers are just random between 0 and 1. Each number is 0 and 1 random number. And this distribution basically is the distribution of this random number is all, the distribution is uniform. If, for example, we want to plot the histogram or the distribution of A, it will look like uniform. Let me just give you one or two plots using matplotlib package, although we will see matplotlib package later on, but let's assume that this is just a plotting package. This is just a package that helps us plotting. Just import that, import matplotlib.pyplot as plt, import that, and after importing that, you just plot a histogram, plt.hist, for example, and pass A, and you can see the histogram is roughly uniform. Everything is equally likely. We can make more bins. For example, we can have bins equals, let's say 100, and we can see almost all the bins, they are just look like uniform. If we make more and more data set, then they will all look uniform. One more thing we can have, for example, this and let's say b equals np.random.rand n, and that generates normal random numbers or Gaussian random numbers, let's say, which the distribution of the numbers is the bell-shaped curve, for example. So let's just plt.hist b and bins, let's say, equals to 200, and we can see a bell-shaped curve because the distribution of this data is Gaussian distribution. It looks like so. So this random package is this np.random is really important package. It has it can create different kind of random numbers following from different distributions. And doing in machine learning or in statistics, sometimes we need to generate these kind of random numbers sometimes for testing purposes, sometimes for adding noise of a particular type to test our model and stuff like so. So it is good to have a good grip on np.random package. Okay, next we see reshape function. One more thing, for example, if you want to create, for example, a two-dimensional array of just random numbers, let's say you can call np.random.rand, and you can just pass two arguments, for example 2 by 3, and this C will be a 2 by 3 matrix. If you see the C, it will be a 2 by 3 matrix of all random values. If you see c.ndim, it will be having the dimensions are 2, and it's a two-dimensional array. further, we can create, for example, a 4-dimensional array. C equals np dot random dot rand, maybe 2 by 3 by 4 by 2, and that's a 4-dimensional array with this particular order. So if you see this c dot ndem, that will be this. Yeah. So let me just give you an interpretation of what that thing is. There are two arrays that are 3-dimensional, and there are two of those. Okay. Now each 3-dimensional array has 3 2-dimensional arrays. Wow. So each 2-dimensional array has 4 1-dimensional arrays, and each 1-dimensional array has 2 elements in it. So that's what this structure is. Yeah, get a good look and feel. So let's see the reshape function. For example, let's say we have d equals np dot arrange. Let's say we have 100 values, and then we say reshape these 100 values to, let's say 4 by 25. So this d will be a 4 by 25 matrix. So if we just get the shape of d, so that will be a 4 by 25 matrix, or a 2-dimensional array with 4 rows and 25 columns. Yeah, so sometimes we want to work on matrices, and we can just plug in these arrange function to generate a bunch of numbers, and then we can reshape those and build a matrix quickly, and then just test the performance of our algorithm or stuff like so. So not only the reshape not only returns the I mean, you can reshape a matrix, and you can reshape an array into more than 2-dimensional array if you want to. For example, arrange 100, let's say dot reshape, maybe as 4 by 5 by 5. It's a 3-dimensional array. Now this d will be a 3-dimensional array containing different values. Yeah, so now you can access it and do whatever you want to do. So not only the reshape, arrange, and permit random, there are other functions as well. np dot zeros, for example, if you press z and you just see the zeros, and then you just press a question mark, you will know what that function is, how can we use it, and so on. Similarly, you can have several other functions. There is an important function ones, for example. You can call that function, and that will generate an array of all ones. You can see how to call that function here. There is np.empty, there is np.empty like. There are so many functions just to create some matrices very quickly, and you want to test your code or algorithms based on those. So yeah, so there are a lot of functions that we want to that we can work on. So next, so there are a lot of functions that can quickly create a NP array and an n-dimensional array. We can quickly create an array, test our algorithm, or use that array wherever we want to wherever we want to use, and we can move on. Just a few functions like arrange, ones, zeros, they are there, or random.rand, random.rand, n, and other functions, they are available. In the next video, we will be seeing the indexing or slicing inside NumPy array, and we will also be seeing the difference of that indexing with or slicing from the ordinary list or the ordinary data structures. What is the difference of slicing in NumPy with the, for example, with the list? We will see that in the next video. Hope to see you in the next video. Okay, here is my favorite topic in NumPy, slicing. Actually, indexing or slicing in NumPy is the way you access subarrays is just the same as the way you access substrings or sublists. And you already have seen how can we use this slicing or indexing in lists and in strings. The difference here in NumPy is in list, for example, if you slice, you get, for example, let's say b equals a 1:5. If you slice that thing from Numpy, then B is not a copy. It is actually accessing the same memory view as in A. Now if you change any element in B, the corresponding element in A will change as long as A is a NumPy array. However, if A is a list or any other data structure, ordinary data structure, then the slicing, this kind of slice, gives a copy rather than a view. So that's an important difference. We need to know that. Rest of the indexing technique is almost the same. You do this kind of indexing. That is how you can reverse. This is start, end step. All the things are same, except how can we play with the two-dimensional arrays. Let's see that. Let's see some examples of indexing one by one in Jupyter Notebook and see how the slicing actually creates a view rather than a copy. So let's go to our Jupyter Notebook and see how can we play with different indices. Let's say A is np.arrange, let's say 100, and let's shuffle them. Let's stay as it is. Let's say that's A. Now A, let's say, let's print some certain things. Let's say B equals A, pick all the elements starting from index 3, ending at index 9. So 10 is not included. That's B. Let's print B. Let's see what's B. So B is this array. Okay. Now what I'm going to do is I'm changing the contents of B. This NumPy array is mutable. You can change the elements inside, no problem. So I'm going to change the elements. Let's say one element in B. Let's say I'm going to change element number 0 in B, which is 3, and I'm just placing that element as -100, -1200. That's it. That's the case. Okay, now the contents of B has been changed. Yeah, but now let's see the contents of A. The contents of A also has changed. That's a big difference between slicing an ordinary list or an ordinary data structure or slicing a list. When you slice a list, you get another label, but that label or that variable is accessing the same memory. The memory actually is not copied. There is one memory view, and these two different names, whether you access those elements using B or you access those elements using A, the same memory is being accessed. If you change the memory using B or A, you will see the effect in both of the variables. So that's one difference. Now, after having knowledge of this difference, if we really want this behavior to not happen, one thing that we can call is we can say, okay, A, for example, A, let's say 3 to 10, and then we can call our famous function, remember that, copy. You can copy that, and now B is completely a different array. It's a different memory view. If you change B now, the effect will not be seen in A. So copy function is there whenever you need copy. One thing, if you are not going to change elements, the NumPy supplies you very fast implementation of slicing by not changing the memory view. If you are aware your algorithm is not going to change the elements, slicing will give you much efficient access to the elements or the sub blocks or sub arrays without actually making the copies inside the memory, which can take time and space both. So this is one plus of NumPy over the other data structure that we have seen so far in Python. Okay, let's play with indices. Let's say, what do you think? What is that thing? Colon 2. What? Or colon, let's say 5. What it will do? It will start from the very first index, which is 0. It will go to the last index, but it will pick every fifth element. So let's see. So it picks 0, then 5, then 10, then 15, because the jump is 5. Great. What do you think? What this will do? Let me just teach you by example what this will do. Yeah, what it will do. Remember, if you apply a minus here, the end and the start and end, they just get swapped, and this becomes a step from the end. So what will happen is the same kind of impact. You start from the very end, then you take the step of -1 from the end, and you just paste every element. So this is kind of reversing the array with kind of steps starting at the end. Great. So another way of reversing the array is, if you want to reverse the array as a whole, just apply -1, which means start from the end and pick every element from the end till the beginning, and the array will be reversed. This element is there, remember that? This is there. Let's change that element. So so A at position, so I want to find out the index where this minus 1200 is located. So IDX is equal to A dot index. I guess there is a function index. Yes and no. Index. Oh, there is no index there. Is there an np dot index? Np dot index. I want to find out the index where so index, there is no index function, indices or something. I want an index function. Is there any index function? I want to find out the index where -200 is located. There are several ways, but I want to find one. So for example, let me see whether there is an index function or not, available in Numpy or not. No, it is no longer there, but there is indices function, I guess. So indices, what that does, I guess that does the same job. Let me see. np.indices returns an array representing the indices of a grid. Okay, so I have to give a grid, and then it returns, for example, the indices of all that grid. How can I use that? Well, it becomes difficult. There may be a find function, or how can I locate the index where the -200 is located? How can I do that? Yeah, very difficult. Seems like very difficult. Oh, why don't I, rather than finding out a function, why don't I just play with NumPy? Why not? So let's say A equals -1200. That gives me a Boolean array comparing each and every element with -1200. So the array, the returning array, let me call the index array, or the Boolean array, let's say B. That array is true or false array, or 0 or 1 array. Wherever there is -1200, that index is 1, that value is 1, otherwise it is 0, completely 0. And then what I do is I just multiply that with the np.arrange with saying that a dot size. So whatever the size of A is. So because these are the indices. Okay, then what? That's the pointwise multiplication. Great. So when I will multiply them together, what I will get is what I will get after multiplication. I will get how can I find out? Actually I'm lost here literally. How can I find out the index where am I? So that will give me what? Let's see. What is B now? The B is just an array. B is just an array, and there is this 3 that is located. So how can I find out where is this 3? How can I again, the problem is finding out the index. Okay, that's really a bad thing. Can I call this a dot indices and just give a -1200 and everything just worked out? No, there is an error. Oh, I'm lost here. Literally, I'm lost here. I need to know how to find out the index where this particular element minus 1200 lies? So that's a question for you as well. I'm also lost. So let's see you in the next video. And we first will solve this problem to finding out the index of a particular element, or maybe a lot of elements. And then we will continue from there onwards to see more indexing. Okay, great. So hope to see you in the next video by first solving the problem how to find out the index of a particular element in a NumPy array, or maybe more than one elements in a NumPy array. And then we will be practicing more about these slicing examples. Okay, hope to see you in the next video. Okay, let's say this element is there, and let's say we want to locate that element in the array. We want to just know where this element is in the array. So array A has this element. Let me print array A as it is. This array A has this particular element, and we want to know where what is the index of this element inside the array. There are several ways of doing this. One way is to find out that index is simply you call the function argwhere, for example, argwhere A is equal to minus 1200, and that will return a 2D array. And if you just want any one index, then you return that kind of thing. So if you write this thing, you will get the index exactly of the element that is there. So the index is 3. If you want to change that value, for example, the value should be 3 here. If you want to change that value, what you can do is you can write okay, A idx is equal to 3, and A is reversed to its position wherever it was created. Okay, great. Now let's play with two-dimensional indices. Let's say two-dimensional arrays. Let's say we have A equals np.random dot rand. Let's say we have 5 by 4 matrix. Let's say a two-dimensional array. Let's round all the values by multiplying them to 10. What it does is, because all the values, this rand function, all the values it generates are the values between 0 and 1. What this multiplied by 10, what it does is it actually scales up all the values to 10, and then round function actually rounds the values to the integers. Now A will be, what's the problem? Round method is no longer there. Okay, maybe there is np.round. Maybe that np.round, maybe np.round is there. Yes, np.round. So round function of np. So this A is this array, for example. That's a 5 by 4 array, 5 rows and 4 columns. So let's say I want to access the second row. First of all, let's say I want to access this particular entry. This particular entry is second row and third column, which means the index is 1, 2, because second row means the row first has index 0, row 2 has index 1. Similarly, column 1 has index 0, column 2 has index 1, and column 3 has index 2. So that is what this particular entry is. What if we want to access the whole second row? For example, we want the second row, so that's how you slice. A normal meaning of this is the row should be 1 and the columns all the columns. So that's how you access the whole second row. If you want to, for example, access the whole third row, for example, or whole second column, let's say, that means you say this, okay, the column number second and all the rows, which means the whole second column that is accessed. And that, if you see, that's the whole second column, 6, 4, 2, 10, and 1. That's what the second column is. Further, once you have you can for example access a submatrix. Let's say you want row number 1 to row number 3, not including 3, and then of these rows you want column number 2 to column number 4, let's say. And if you do that, you access the whole submatrix. First, it actually picks row number 2 and row number 3, because row number 2 starts from 1. And then of those rows, it picks these columns, and you can just pick the submatrix inside. You can do a lot of processing on these matrices. For example, this is matrix A. If you just type A dot transpose, that T is for transpose, the matrix just is taken transpose of it. Further, there is a complete library, linear algebra library in Numpy. For example, if you just import Numpy dot linear algebra as LA, for example, then this linear algebra library in Numpy has a lot of functions: eigenvalues, Cholesky decomposition, computing determinant of a matrix, finding out inverse of a matrix, and whatnot. For example, let's say we have LA dot inverse, and here is np dot random dot rand, let's say some 3 by 3 matrix. So what it returns is, it returns the inverse of this matrix. And this linear algebra library, and there are other libraries as well, but this is one scientific library that maybe most of data science experts who actually want to do research, they might be thinking this linear algebra library that specifies a lot of functions related to these matrices or two-dimensional arrays. So that is there. Okay, so that's about indexing. We can play with these indices a lot if we want. One more thing, just one last thing. Let's say this is our A, and what we want to do is, let's say we want to sort this A with respect to the columns. We want each column to be sorted individually. What we can do is we can call sort function, and we can pass x is equals 0. X is equals 0. That means sort all the columns individually, and the result will be, if you see the result will be every column is sorted individually. If we want to sort, for example, every row individually, we will say, okay, sort x is equals 1, and every row will be sorted individually. And if this is a multi-dimensional array, more than 2 dimensions, then x's can be 2, x's can be 3. So with respect to whatever x's you want your sorting can happen, it can do that. If A is one-dimensional array, then dot sort function without an axis just sorts the one-dimensional array from beginning to the end. And if you want a descending order sort, just sort it first and then reverse it using indexing. Great. I mean, there is a lot to discuss. I'm ending this slicing here. In the next video, I'm going to show you kind of masking, or sometimes called the fancy indexing, that is much more powerful and useful in a lot of different contexts. So hope to see you in the next video with more NumPy indexing. Okay, there is another way of indexing a NumPy array. In the last video we saw we can do slicing notation, for example, start from here, end at here, and stuff like so. There is another way of accessing a NumPy array, as we have an array A, and we can just give an index array inside. For example, let's say A is one-dimensional array, and then we just give 1, 4, 6. That means pick the element at index 1, pick the element at index 4, pick the element at index 6. So this kind of array inside can be a list or an array that is called an index array. And you can just pick the elements that you want to pick. For example, you want to pick all odd elements. You want to pick first element, fifth element, and 17th element. You can just create an index array and pass it and index and access your elements using that index array. That's possible in NumPy array. Further, you can access different elements using a Boolean mask as well. So Boolean array, for example, true, true, false, false. Wherever there is a true, pick that element. Wherever there is a false, don't pick that element, and return the elements that are picked. For example, assuming here that you have an array A, which is one-dimensional array, let's say, assume that has 8 elements, 1, 2, 3, 4, 5, 6, 7, 8 elements. Now you pass a Boolean mask inside where with obviously 8 elements, 8 true or false values. Wherever there is true, so pick the very first value, pick the second value, don't pick the third value, don't pick the fourth value, pick the fifth value, pick the sixth value, pick the seventh value, and don't pick the last value. So that is also possible in NumPy. One thing that is important is if you do this kind of indexing, which is sometimes called masking. If you do that, if you supply an array index or index in a Boolean form, you by default get a copy as compared to slicing. In slicing, you get a view that's a separate copy. You need not to call a dot copy function. It is by default a different copy. And this is a difference between the ordinary slicing that you do. For example, start from 1, go till 50, take a jump of, let's say, 2. If that is your indexing style, that is called a slicing. The return value is a different view having the same memory. However, if you use the array index or the Boolean array called masks, then you get a copy rather than. So which means if you get a new array, you change the elements in the new array using the array indices, you're not getting that change happen to the original array. So that's the difference between slicing and masking. Okay, this kind of Boolean indexing becomes really handy. For example, what if you want to get all the elements that are smaller than 8? One way to do that is just write A and then apply a condition. A is less than 8. Well, A is less than 8 will create a Boolean array, and everywhere where the element is smaller than 8, there will be a true, otherwise it will be a false. Now the inside array is a Boolean array, and you access all the elements with respect to that condition. So it will return all the elements that are smaller than 8. How fancy is that? Further, you can have these conditions in a combined way. There is one difference. There is an AND operator, and there is an AND operator in a different way. So I'm going to discuss the difference of this AND and this AND as well in this video. So let's go to Jupyter Notebook, our friend, and see how can we play with this masks. So let's say A is again np.arrange, let's say 100. That's our A. And what we now do is we access the elements of A. We access, for example, the third element and the fifth element and the sixth element. Let's say we want to do that. And that's our B. Yeah, so that happens, let's say. So what B is this. Something that you need to know is if you change the elements of B now, because that's a copy, let's say -4, that change does not happen in A. That happens in B for sure, but that doesn't happen in A. A does not contain any value that is -4 because using these kind of indices, the array index, by default, the result is a copy rather than a view. Further, let's say you have this A and you want to access all the elements that are smaller than, let's say 40. Access all the elements that are smaller than 40. So that is possible. Now B will contain only the elements that are smaller than 40, all the elements. Wow. Further, if you want to access all the elements that are smaller than 40, and they are bigger than, they are smaller than 40 and they are bigger than 30. Let's say you want to access all the elements that are between 30 and 40. You can just access those elements like so. Oh, there is a problem. A.any, A.all. What's the problem here? The truth value of an array with more than one element is ambiguous. Use A.any or A.all. Okay, this A is less than 40 is a Boolean array. A is greater than 40, that's a Boolean array. So what's the problem? Why can't we not use this? Or what's the problem? We should have used that. So use and yeah, I guess we were missing these brackets because it might be confusing this 40 with this A and stuff like so. So use parentheses. Great. Now B contains only the elements that are between 30 and 40. Now one thing, what's the difference between this particular and this symbol and? The difference is this and, A and the and operator, it is used when both of the sides of this and has one is one object and it has one true value, either true or false. And this particular symbol is used when the left side and the right side can be arrays, and each element of that array can be true or false, and so you can think of this and is used in arrays. However, this is used when both the sides are single objects. So that's the difference. Other variants of and, I mean, the and is like this, that these are the same things, but remember the use. This is used for arrays, this is used for single objects. Similarly, there are other symbols like or, that is used this way, or that is used that way. Similarly, there is a not for arrays is used like this way, and not for otherwise is used like that way. So remember these, the left side kind of symbols, they are used for arrays. The right kind of symbols, they are used for single objects that has true or false values. So this kind of masking is really powerful. Later we will see in pandas accessing different kind of data with particular kind of conditioning. That becomes really handy if we are comfortable with these kind of indexing, and that's really powerful indexing. Okay, I have told you the difference here between and. I've told you that this is copy rather than a view. So just bear with me some more time on Numpy, and I will tell you some more truths about Numpy, and then we will move towards another package called pandas. So before pandas, more Numpy is coming. Hope to see you in the next video. Okay, in the last video we saw masking, which is sometimes called the fancy indexing as well. And here we are going to discuss one more feature of Numpy, which is a very powerful feature called broadcasting. Think, for example, you have an array, let's say 2, 3, a matrix, let's say two-dimensional array, 2, 3, 5, and 9, and you want to add, in every element you want to add a number, let's say 5. So one way to do that is create another array with 5, 5, 5, 5, and just apply this add operator and you are done. Great. But this Numpy allows you to just write, let's say this is array A. Numpy allows you to just do this particular thing, and this 5 is automatically broadcasted to match with the dimensions of its other operand, and the addition happens. You need not to do this explicitly. And this broadcasting is not just one scalar value. For example, if you have one variable, let's say A is this, and you want to add, for example, this particular column, let's say 1, 3, you want to add this particular column in the first column as well as in the second column. But then you need this 1, 3 to be copied again and make a bigger array, and then you do that. Well, broadcasting allows you, if you just write this as A plus 1, 3, it will be automatically broadcasted to match the size of the other operand. Wherever the broadcasting is possible, there are certain rules to know when broadcasting is possible. It is not possible each and every time. For example, if you have this matrix 2, 3, 9, and you have 4, 2, 1, let's say this matrix, and you want, for example, 2, 1, and 6, 2, for example, if you want to do that, the broadcasting may not happen because in this way, if I want to broadcast this structure should be, if this structure is broadcasted to in horizontal way, the two columns will be added and the addition cannot happen. If it expands to a vertical way, still the addition cannot happen. So this here you will get an error because broadcasting cannot happen. But in several cases, when you want to add, for example, a scalar multiplier with a particular thing, wherever possible, this broadcasting is possible. And broadcasting is just it's just a feature of Numpy that allows you to not repeat to match the dimension of the other operand to apply a particular operator. It does it by itself. Great. Next, we see some more important functions to know. One is horizontal stack. That means if you want to concatenate two arrays that can be concatenated together horizontally, you can call hstack function, and that will concatenate the two arrays together and returns another array. Similarly, vstack is if you want to concatenate two arrays vertically, if they can be concatenated vertically. Similarly, there is another powerful function, sort, and there are a lot of other functions. These kind of functions, they are called universal functions, and they are very, very, very powerful, very, very fast. Their implementation is vectorized. Vectorized mean the implementation, the all loop kind of layer is deferred to at the compile time, and the things are really faster when you do a vectorized code. So having said that, it is always recommended to not use explicitly for loops to achieve these kind of results. Whenever a universal function is available, use that, because the efficiency of that universal function will be way, way, way more than whatever loop or whatever function you will be writing other than the universal function. So, and by the way, there is another function, concatenate, as well, in which you can specify x's, and it will either act as horizontal stack or either act as vertical stack, depending upon whether the x's value is 0 or 1, whatever. So let's just get comfortable with these three functions just quickly in Jupyter Notebook and see an example of, let's say, broadcasting as well. So let's say we have a function, let's say we have an array A. A is, let's say, np.random.rand. Let's say that is 2 by 3. And then I just multiply this with 10. Remember this thing, and then we just np.round. We just round everything so that it becomes whole in this particular way. Okay, that's A, let's say. So that's our A. That's the, now if we say A plus 3, the 3 will be added everywhere in A, and that happens through broadcasting. Wow. If we do, for example, A plus, for example, np dot arrange, let's say, just 2 values, and then we just reshape it to let's say 2 by 1 matrix. If you do that, then still what will happen is, just apply the parentheses just to show that this should happen first. What will happen is there will be a column that will be added to every column in A, and that again will be happened through the broadcasting. So broadcasting is that powerful. Next, let's see the stack. So let's say this is A. Let's say we have B, that's another array. Let's say np.random.rand. Let's say that new array is 2 by 2. And again, let's say it is multiplied by 10, and np.round, just to avoid the decimal points. Let's say this is B. Now A is a 2 by 3 array, B is a 2 by 2 array. If I just concatenate them horizontally, I will get another array which will be 2 by 5. So C equals np.hstack, horizontal stack, hstack, and I will call these A and B. One thing that you need to know is, if you want to call this hstack, horizontal stack or vertical stack, these arguments A and B that you want to concatenate, you have to give them in a tuple, or you may want to give several values to concatenate together. Maybe you have 10 matrices to concatenate together horizontally. You have to give all these as a tuple inside. Okay, great. Now similarly, we can do a vertical stack if we want, one on top of the other, and we can call a concatenate function as well if we want. Third is a sort function. For example, if we want to use np dot, let's say A is np dot random dot permutation. Let's say np dot arrange. Let's say the 10 values. Let's say that's our A. Let's say this is A, and we want to sort this array. Oh, this is already sorted. Why? Is it sorted? No, it is not sorted. 1/4, it is not sorted. Yeah. Let's say we want to sort it. A dot sort. One way of doing that is just call a dot sort and you are done. That's the value of A. Another way, which is sometimes more readable, although exactly the same, is to use a universal function using np dot that thing. That also is the same thing. Now sort by default sorts in ascending order. If you want to sort in descending order, then what you can do is you can sort a dot sort, for example. You do that in ascending order. Then what you do is you just reverse it. -1 and just copy that in A again. Now A will be sorted. Wow. Sorted in descending order. Yeah, great. One more, just to give you one more flavor. If you create an array, for example, np dot array of strings, for example, A, B, C, and another string is how are you, and maybe we have another string U785, and maybe we have another string 13ER. Let's say that's a string. That is possible. As long as all the objects have same type, you can create an NP array. Now you might be wondering, what will do this sort function on A, because these are all strings? Well, the answer is it will sort the strings according to the alphabetic order, whatever the alphabetic order is. Whatever string according to the alphabetic order should become first, that will become first, and the other strings, they will just join. Yeah. So yeah. So that's about something that is not the numeric value. Okay, great. There is a few more things to come about NumPy array, and then we will be moving towards Pandas library that is built on top of NumPy array for better processing of data. Hope to see you in the next video. Okay, in the last video, we saw horizontal concatenation, vertical concatenation, sort function. We also saw some broadcasting and stuff like so. Universal functions, it should be speed here. Sorry, it should be speed. Universal functions are really speedy. I always am talking about NumPy. Whenever I start NumPy, I said it is fast, it is fast, it is fast. I never show you how fast that is. So let me give you an example. Let me just create an NumPy array with a lot of numbers, and then just apply an ordinary function. Let's say I want to add all the numbers in this array B. Let's apply an ordinary function that is not in NumPy, and then let's use a universal function .sum and see how speed difference is there. If, for example, we apply a universal function to achieve a particular task, how speedy that universal function is, because the vectorized implementation, as I told you, is much faster. How faster? Let's check that out in Jupyter Notebook. That's a magic command, time it, that will tell us how much time this particular task has taken. And if you run this command, it will call this function again and again several times, and then will report an average value that will be much more stable than just calling once. After that, we will also write our own sum function using loop, and we will see whether that is even closer to a universal function speed or not. Let us just check the speed of universal functions. That will give you a look and feel of how much NumPy implementation is faster. So let's say we have an array, let's say B, np.random.rand, and let's say that array is huge, really huge. That's it. That's the case. Now what we do is let's say we call a function sum. So let's say we call a function sum. That's a built-in function in NumPy. That's a built-in function. That's a built-in function in Python, not a NumPy function. And then let's say we do the same task using NumPy universal function np.sum. That's the same as np.sum is the same as if we write, for example, b.sum. So whether you write b.sum or you use np.sum and b pass as an argument, both these things are roughly the same. So let's run it. It will take a while. It will take a time because okay, the sum function takes 307 milliseconds. That is not a universal function in NumPy. That's Python function. That is not written in NumPy. That is not a vectorized code, nothing. It takes 307 milliseconds to take the sum of the elements of this array. And it does that by applying 7 runs, 7 loops. However, the universal function takes just around 3 milliseconds, 2.7 milliseconds. How are you going to compare this 307 with 3? How much faster you are? Around 100 times you're faster. Yeah. This NumPy is literally faster. NumPy, the universal function, they're faster. Maybe you attempt to know that, okay, this sum function might be too slow. Let me write my own function. To do that, let me define my sum, and my sum just take an argument, let's say something, let's say G, and what it does is for, let's say S equals 0, what it does is for X in G, S plus equals to X, X plus equals to X, and then just return S. That's it. That's your function. Let's say you think that this is really a great function. Let's do that. Okay, let's compute the time for this. Time it, my sum, and let's pass the array B and see how faster this is. This is roughly the same as you're calling the sum function, but this np.sum, or the universal function, is way faster, way faster. So use universal functions, avoid for loops, avoid your own functions if the same task can be achieved through universal functions. Whenever possible, avoid loops when you are working with NumPy. That's a serious suggestion. Follow that, because the universal function written in NumPy, they follow the vectorized code. All the interpreted slowness that is deferred to the compilation layer, and the NumPy becomes really faster and shows its power when you are working on large arrays using the universal functions. So I can speak more about NumPy, but I have told you some basics of NumPy, and we end the NumPy here, and from the next video we will be moving towards a very fancy and beautiful kind of package called pandas to handle data. And by the way, the pandas library, the pandas package, completely is built on top of NumPy. Everything that is there in pandas is built on top of NumPy. So all the indexing and all kind of stuff, slicing and speed, all is there in pandas that is due to the NumPy. So we will see one more package after pandas, which is matplotlib for plotting afterwards. And we'll do a project at the end using scikit-learn as well, just to wrap up all these things together. But for now, I'm ending NumPy here, and in the next video we will start pandas.